All right, let's do our exam review for AP2 and Physics C E&M. So how this video is going to work is it's going to be a bit different than the video for P1 and APC. So this is less of an exam strategy video, because if you've taken this as sort of a second year course, you're probably familiar with how these exams work. Now, if you want to know some multiple choice tips and those sorts of things, you can watch the other video, but this is more of a content speedrun. So we're going to start by doing a review of kind of all the E&M P2 shared units. So that would be E&M without calculus. We're going to do some multiple choice questions that come up frequently. And then we're going to go into more like things you should remember for each of the courses. So we'll do an E&M section hitting on the calculus aspects. And then we got some stuff for P2 relating to thermo, optics, waves, and modern. And then we'll end with my probably wrong predictions of FRQ topics we haven't seen for a while that I think might be due, and kind of how I think stuff gets split up. So, again, I have no knowledge of what's going to show up, so I'm probably wrong. But it's always fun to predict. So, timestamps are there for you to click around. All right, so multiple choice. Got 40 multiple choice questions, 80 minutes. They're split into simple math, number math, ratios, comparisons, claims, and justifications. The physics algebra-based classes do a lot less of the sort of deriving symbolic expressions compared to physics C. That's sort of the main difference. So there's a lot more just like select the right answer, which is your claims questions in P2, versus there's a lot more derives in E&M. Some graph relationships that are useful in both courses. You could plot charge as a function of time, which slope gets you area. You could graph current as a function of time, whose area gives you the charge. Now, this is a strange one. We graph I versus delta V because that's how Ohm's law appears on your formula sheet. So the slope is actually resistance, or 1 over resistance, not resistance itself. And there's some reasons behind that because usually in a lab you can change delta V. You don't get to pick I whatever to be whatever you want. So that's kind of why we have that. Then if you're graphing electric potential, the slope of electric potential via position is the negative of the electric field, as E field points to low potential. And then the electric field, the area under that graph, is therefore the potential difference with a minus sign. And lastly, if you take the magnetic flux, slope of that graph gets you induced EMF via Faraday's law. So the first unit, this is a lot of points, is electrostatics. So the main issue with electrostatics is there's these 4 quantities that are very similar sounding. So we have electric force, that's the actual push or pull. And remember, forces require 2 objects. So that's a 2-object interaction. Electric field is the direction of force that a positive charge would feel due to that charge if you placed it there. So this is your sort of sources and sinks. So you need a single charge for an E field, sort of the influence that a single charge would have. Electric potential energy, this is the energy associated with 2 interacting charges. Because again, potential energy is associated with a force. So that's going to be a 2-object interaction. So it's positive for like charges because it costs you energy to bring the positive together or negative together. Or the potential energy is negative for opposite charges, since opposite charges want to attract. So you have to pay them to separate them. Or why is the assembly energy negative? Well, if you just let the charges come together, they'd be speeding up with kinetic energy. So that must mean if they're stopped, you must have somehow stolen their kinetic energy. Then the energy per charge is called potential, and that's your sort of height. We like the hills and valleys analogy for that. And to go across these concepts, we can say that the field points downhill. So positive charges like to go to valleys, which makes sense. So positive charges just behave like regular old mass where it'll go downhill. Here's a nice little flow chart for us to look at. This shows you all the relationships. We got different numbers of Q's, and some of these quantities are squared, some aren't. This works for a uniform field. If it's not uniform in physics C, you have to transform the cross relationships into derivatives and integrals. Some common MCQ types, you might have to compare the forces two charges exert on each other, which is equal and opposite by Newton 3. You can imagine we put charges on a line or in 2D, and you have to do something about one of the four electrostatics quantities. Sign of work, that's a big one. We look at the sign of the work done by the field versus the external force. Then you got to do some energy conservation, knowing that kinetic energy is opposite the change in potential, and potential energy change would be Q delta V. And also you have to analyze isolines or equipotentials, using the fact that E points downhill. Since E is the steepness of the terrain, where your terrain is closer together, your height drops, that means that it's a steeper push. So let's just do some examples. Two charges are placed along the line shown below. All tick marks are equally spaced. Where is the magnitude of the net electric field the greatest? So what is E field? E field, that's sources and sinks. So it's the push caused by each charge. So I like to do this with color coding. So there would be a big source that way. There would be a big source that way. Actually, I need to make this smaller because I'm going to go over my lines here. Big source that way, big source that way. Right, you can think of positive charges as sort of emitting fluid. And then E field decreases with distance. So we get smaller and smaller sources as we go along. Then for my minus Q, that's a sink. So we'd get a large pull, but not as big as the 3Q near that. Another large pull, a smaller pull, and then an even smaller pull. So we can see just based on these arrows here, the fields are adding in this middle region, and the field would be greater at B because the 3Q charge is bigger, so it's a bigger source. So the fields do add at B and C. It's just B is closer to the stronger field. All right, same question, except it's potential. So we'll see if we can just do this one real quick conceptually. So we said potential, that's height. So where's the height the greatest? So this is a tall hill, and this would be a short valley. So where is our terrain the biggest? Well, you can also think about this in terms of the sort of height contributions. So you get a huge positive height contribution near the hill, and then the positive height contribution slowly decreases. And then from the valley, you would get a negative height contribution. And it's not going to be as big. So you get something like that. And I can make it maybe a bit more obvious, but the answer is A. The answer is A because you're the closest to the hill and you're the farthest from the valley. So the hill is sort of shielding you from the valley on the other side. So you don't get to feel its influence as much. And if you just draw this like topographically, I guess would be the word, you draw like a big spike and then like a smaller spike, and you'd see the height is greater there. But pretty standard question. So just be very careful about what word we're asking about. Is it field or is it potential? All right, now of course we got to do another. Charges are placed at the vertices of the square shown here. What's the magnitude of the force exerted on the plus Q charge? So negative attracts positive. Positive repels positive. So we're just asking, what is 1 plus 1? Trick question, 1 plus 1 is square root 2, because this is Pythagorean theorem. So we have a force, we have KQQ over S squared. Left, we have KQQ over S squared. Down, so the hypotenuse is therefore going to be the right triangle constructed there. So F is just going to be I don't put letters in your square roots because you know the units are going to work out, right? I know force is going to be some multiple of KQQ over S squared. And then just do the Pythagorean theorem with the numbers. So this is one copy of KQQ over S squared. This is one copy of KQQ over S squared. So I have 1 squared plus 1 squared, which is, of course, 2 under the square root. Making that C. Also, something I didn't say that comes up quite often that I missed with charges is remember the shell theorem. So if you're given like spheres, shrink them to dots. Center to center distance only, please. All right, and now we just got to get our fourth quantity, and this time it's potential energy. So we know that potential energy of the system U is the sum of KQQ over R. So let's just figure out each sort of contribution there. So this contribution, this would be an energy debt. It's a positive and negative. So this would be negative KQQ over S. Now this would be an energy cost to bring these two together. So it'd be a positive KQQ over S. So those actually cancel. But wait, it's not 0 because there is still a third interaction. We have to remember to do all different pairs of this. So we also have to remember to pair up the diagonal. So it's negative because they attract. Oh, and I need to fix my Q's here. How will we salvage this? Like that, I suppose. KQQ over S. And so it's going to be KQ squared over, what's the distance here? So it's not S because that's the side length. So I'm at a right triangle with S and S. So by 45, 45, 90, that's just S times square root 2. Right? The diagonal has to be longer than the side length. So it's answer choice B once I actually make the units work out right. So let's actually take a quick moment and fix this. So I need to square the Q on top. Good thing I have a white markup tool here. So KQ squared over S over root 2. All right, first mistake. Hopefully not many more. Obviously I gotta fix this slide too, but we get the idea. Two charges of opposite sign are slowly brought together from far away. What's true about the sign of work done by an external force in bringing these charges together? So by definition, the net work done on a system changes the potential energy. And also take this as a fact or memorize this if you don't want to deal with the dot product definition. The electric field always does work exactly opposite to the potential energy change. So what we have here is we have two opposite charges. They're starting far away, and then we bring them close together. And we just want to figure out what's happening to the potential energy of the system. So if they're very far away, there is no energy between them, right? But if we bring them together, there is potential energy between them. They're an energy debt. They're not going to be separated. So we're going to have a negative potential energy. So that allows us to quickly select the right answer because we know the work done is exactly equal to the change in potential energy because where did the work come from? Where did the energy come from? Well, the work, right? If I started from no energy and ended with negative potential energy, I must have given that negative potential energy to the system from the external force, so it's negative. And then the work done by the E field is always just against that. All right, proton is launched in the plus x direction with 1,000 EVs of kinetic energy. What's the kinetic energy of the proton upon reaching x equals 4? So we know that delta V along an E field is negative ED, right? Because E points to low potential. So if you go with the E field, that's towards negative potential. But of course, E is not constant here, so this really just means we're taking the area. So what's the area? Well, this is just a triangle, so it's 1/2 times base, which is 4, times the height, which is 200. So that's half of 800, which is 400. So this means that the electric potential decreased by 400 volts. So we can use the fact that the change in kinetic energy is opposite the change in potential, which is negative Q delta V is potential energy, right? Q delta V. And a proton has a charge of +1 elementary charge unit, and V was 400. So we get 400 EVs. Negative 400 EVs. No, negative, negative, so it is positive. Because our potential difference was negative 400. So what this tells us is that our proton actually speeds up, which you could have figured out because I'm going with the E field. Even though the magnitude of the E field is changing, I'm going with the E field the entire time. So I do know that my charge should be speeding up, so the kinetic energy change is positive. So it's just my starting kinetic energy plus the delta, right? Because final thing equals starting thing plus delta. So I get 1400 EVs. All right, now we got nice straightforward equipotential analysis here. So remember that these are equipotentials, meaning same height. So everything on this sort of 2-volt curve represents any charge at that curve will have the same potential energy. Then we have 3 volts. So anything on the 3-volt curves will have the same potential energy. And then anything on the 4-volt lines will also have the same potential energy. So it costs 0 work to kind of move along one of these same colored curves. And we're interested in finding where is the field stronger and what is the direction of the field. Well, we do know that E points downhill. So if I want the direction of the field at B, I need to figure out how to get to low potential. So B is currently at the orange curve. So I have to, and it's perpendicular. So I'm going somewhere along this line, and the red curve would be plus potential. The blue curve would be minus. So I am going downhill. So the E field points to the right. And then where is the field stronger? Well, since E field is the slope of the terrain, we're looking for lower spacing, and the equipotentials are clustered closer together at B also. So it's right and B. All right, next part. This is like electrostatics part 2. It's just talking about charge transfer or conductors. So if you transfer charge, it's always equal and opposite. You can only transfer electrons whose elementary charge unit is given. All objects will polarize due to a charged object where the pluses and minuses sort of shift, meaning neutrals are actually attracted to both. So just because an object is attracted to a charge doesn't mean that object is charged. It could be neutral. Repulsion is kind of the only way to for sure figure it out. And you can't transfer charge unless if you're touching or if the object is like grounded. Now this is really important. Conductors. In a conductor, charge can move wherever it wants. So as a result, the charges get as far away from each other as possible, meaning all charge goes to the surface, meaning there's no charges hanging around inside, excess charges at least, meaning there's no E field. Because if there was an E field, the charges would still be moving. And we know that's not happening because this is electrostatics. So this like equalizing thing happens extremely fast. So E is 0 everywhere in a conductor, but it's not 0 at the surface. It's an equipotential, so E is perpendicular to the surface, and E is stronger at sharp points. So if your surface is curved, wherever there's that sort of tip, that would be the stronger E field point. Think of it like a lightning rod. V is constant as a result, because E is the slope of the terrain. So if your terrain has no slope, it must be perfectly flat. Now, it doesn't mean you're flat at sea level, right? You can have a plateau on a mountain. So potential is probably not 0, unless if we do some really weird definitions. But it is constant. So E is 0, V is constant. If you see a conductor, write that every single time. And if you're inside a cavity, this is more of a physics C thing. If you're inside a hole in a metal, E is 0 no matter what from external fields. Unless if there's something in the cavity with you. So this is like a lightning strike hits your car, you're going to be protected in the car. But if somebody shocks you in the car, then obviously you could feel that. But you're shielded from outside influences. Now, the main principle for these conductors is that V has to be the same. So they don't share the same charge, they share the same potential. So if your conductors have different sizes, or a special case being a capacitor, which can store different amounts of charge to get the same potential, charges don't share equally. It's the potentials that must match. And if you connect capacitors to each other, they really just make one big capacitor. So if there's no batteries involved, two capacitors connected to each other is actually parallel, even though it might look like series. So you can actually just add their capacitances and add their charges to get the new voltage, as long as you're adding the charge kind of on each top plate. And last thing you'll have to do with these conductors is we're really interested in changing capacitance somehow and asking about charge, energy, potential difference, any of that across a capacitor. So remember that if your capacitor is isolated, it has constant charge, right? Isolated means not connected to anything. So where's the charge going to go, right? But if you connect a capacitor to a battery, it has constant potential difference because batteries force potentials, so charges wouldn't be the same. And the E field is also uniform when the capacitor is isolated because we assume that the field is constant and is independent of charge. Now, if you do change the capacitance, that's going to change Q or delta V, depending on which one is constant, and that's going to affect the energy somehow. So some common questions you're going to want to know is charge transfer, sort of how much electrons go from this to this, polarizing questions, E and V with conductors, the two-sphere connection problem, the two capacitor connection problem, and then those sort of ratios or change factors when you do stuff to affect capacitance with isolated and non-isolated systems. So here's a classic. A positively charged rod, you can read the picture. So we have this setup, and in scenario X, we bring the rod close, then we snip this grounding wire. So that's X. And then in scenario Y, we move the rod really far away, then we snip the grounding wire. So the order changes. So let's see what happens in X. So this might be a picture of X right now. So what happens? Well, we're connected with the ground, which means the ground is going to help this sphere do what it wants. So what does the sphere want at this time? Well, at this time, we have a positively charged rod. So the sphere, negative charges in the sphere would really like to get close to the rod. So much so that negative charges actually get dragged out of the ground. So the sphere is negatively charged at this moment. And then as a result, if we snip the wire instantly, that means we're going to end with a negative charge on the sphere. So it's going to be negative in scenario X. But then in scenario Y, if I just remove the rod, from the system, well, the negatives don't want to just stay on the sphere, so the negatives are actually going to just go back to the ground. And then if I snip it with the wire far away, with the rod far away, it's business as usual and it stayed neutral. So it's actually C. So you have to be careful. Order does matter here between the two. So the sphere charge is negative in X, and it is neutral in Y. So lots of variants of this question show up. All right, metal sphere. Okay, I've just stopped. I see metal sphere. So as soon as you see metal or conductor, wherever the conducting region is, you can say E equals 0 and V equals constant. All right. Which of the following is true about the E field and V at point P, which is in this sort of cavity? So it also does say there's an E field directed up that's not shown. So the sphere is sort of placed in an external E field. So we want to figure out what's going on there. Well, it doesn't matter that there's an external field because of what we called shielding. So we know that in any conductor, E is 0 and V is constant. Now, in the cavity, I could change those things if there was somebody in the cavity with me. Like if there's a positive charge here, that obviously is going to generate an E field, but there's not. So what this means is that whoever's in the cavity is just ignorant to the outside world. They're completely protected from external fields. So the field is 0, and then the potential, well, the potential can't change if there's no E field. So the potential is whatever value it was everywhere else in the sphere, which is constant and non-zero, because V is not 0 in a conductor. V is only 0 very, very far away in these types of problems. All right, now we got the two-sphere system. We have two spheres of charge Q. One of the spheres is bigger, has twice the radius. We connect them. What's the new charge setup? So what we know is that the potentials must match. And potential is KQ over R. So KQ over R for the small sphere must equal KQ. Let's actually line it up. Must be equal to KQ over R for the big sphere. So the big sphere's KQ over R potential must equal the little sphere's KQ over R. So now we can do some canceling. The K cancels, the R cancels. So what this says is that Q2 is equal to half of Q1, which makes sense. So in these sort of connected problems, your big sphere will hold more charge, because you have to, if your radius goes up, then the charge has to go up to get the same potential. But that's not enough to solve. Well, technically it is based on my choices. But now you just need to say that the total charge must be constant. So the two charges of the sphere added together must be the original charge of the system, which was 2Q, because each of these had a Q. And we said that Q2 was half of Q1. And we're actually interested in solving Q1. So it's actually a lot easier to say that Q1 is just going to be twice Q2. So 2Q2 plus Q2 equals 2Q. Wow, what a lovely tongue twister there. So 3 times Q2 is equal to 2Q. So Q2 is equal to 2/3 of Q. And I said you could actually figure this out from the answer choices because notice that 2/3 Q is the only thing that's lower than half the system charge. So we know that the bigger sphere requires more charge than the smaller sphere. So the bigger sphere actually takes up more than half of the system charge. So since this was the only answer that was less than half, we knew that had to be the answer. All right, now we have the capacitor version of this. So we have a capacitor with capacitance C, and the voltage across it is V0. And then it says we're going to connect this to an uncharged capacitor with capacitance 3C. And we want the equilibrium voltage across the capacitance C. So once again, V's have to match. And since the V's have to match, that means their Q's won't. So since these are in parallel, we can actually do this really quick. Because if they're in parallel, we can just sort of model this, because we know if we tried to color code our potential when they're in equilibrium, the potentials have to match. So we could actually say delta V across each capacitor is the same, and it's equal to the total charge on the system divided by the total capacitance of the system. So the total capacitance of the system, that one's easier to find. That's just 4C. Now what's Q total? So we don't actually have Q, but we can find it, because we have the relationship for a capacitor that says Q on a capacitor plate is C times delta V. So that actually means our charge we have to work with, which is just on the charged capacitor, would just be CV0. So we see this, the C divides out, and we're left with a 1/4 in front. There is like a more involved way of doing this, where you could have like done the same approach. You could have said the voltage across the first capacitor has to equal the voltage across the second capacitor. And then you could also say the charges have to add up. Solving this system does give the same result, because, or sorry, 3C. This is 3C, not 4. Because you would end up seeing that the first capacitor only needs a third of the charge of the second. So this is really the same problem as the 2 sphere, right? We have a voltage equal equation, and then we have a conservation of charge equation. So it does work. All right, and now we have our pulling apart question. Parallel plates, charged and isolated, the plate separation is increased. Which of the following is true about the energy stored? So if I'm dealing with an isolated capacitor, this means that Q is constant. So because of that, that means the helpful energy formula is going to be U equals 1/2 Q squared over C. And I know that the Q is constant. So I just got to figure out what's happening to C. Well, we also know that for a pair of plates, C equals kappa epsilon naught over D. And we're increasing the plate separation, so therefore capacitance must decrease. So we have the same charge, but capacitance is decreasing, so we have a lower denominator, so that means U increases. So why does U increase? Well, definitely doesn't increase because the charge increases, because we just said Q is constant, so by default it's got to be A. And you actually could have just reasoned that, right? Because do these plates want to be moved apart? No, there's an electric force attracting them, so I have to spend work to separate them, and that stored energy goes to the field. All right, circuit time. So to solve any circuit, you need some combination of these facts usually. Delta V equals IR for a resistor, of course. Series have the same current, parallel has the same potential difference. And if you're given a complex circuit, find the equivalent resistance first, find the battery current first, and then knock out any voltages you can, and just fill out from there. So we do have 2 rules. We have the loop rule, which in most cases just says if you walk all the way around the loop, all of your drops have to equal the battery. And the junction rule says that current splits up. The current splits up at junction points, but it must always remain constant, the total at least. Now, if you do the same thing with capacitors, without putting resistors in yet, capacitors in series have the same charge, capacitors in parallel have the same potential difference, and you use some variant of Q equals C delta V, or delta V equals Q over C to solve for what you need. So you can make some parallels with Ohm's law here. Now, if you do put resistors in, we know that capacitors act as wires at short times, which creates high currents in your circuit. And then at long times, the capacitor is a gap, which is a low current. But at a long time, don't assume all the battery EMF is dropped across the capacitor, because if there's other resistors still in a loop, you're going to be dropping some portion elsewhere. And the characteristic charging or discharging time is this time constant. So it's the time required to become 63% charged from 0 or 63% discharged, which means you have 37% of the total remaining. Because 100% minus 63% is 37. All right, let's look at our common multiple choice types. So we could have resistor geometry, we could have Ohm's law with graphs, we could have resistor circuits, we could have combination capacitor circuits, we could have steady state RC, we can have time constant RC. So first, cylindrical wire made of length L and radius A has resistance R. What's the resistance of a wire of the same material but twice the length and twice the radius? So our formula is resistance equals resistivity, which is a material property times length divided by area. So I'm always going to use my multiplier approach for this, where I just rewrite the formula, and then I do my multipliers. So the material is the same, so same resistivity. The length is doubled, but then the radius is doubled. Radius, that's not area, right? Because area is pi r squared. So actually, I'm doubling the radius, but the double gets squared because of that square. So area actually goes up by 4. So I actually divide by 4 on the bottom. So my multiplier is 2 on top, 4 on bottom. 2 over 4 is 1/2. Be wary of the area scaling here. All right, there's a couple neat ways of doing this problem. We have current versus potential difference for a resistor. What's the power dissipated by the resistor when connected to an 8-volt battery? So power, there's 3 expressions for that. There's I delta V, which is the formula sheet one. There's I squared R, which is an Ohm's law substitution. And there's delta V squared over R, which is another Ohm's law. So I got to figure out two of these circuit quantities. And my graph doesn't go out to 8, although you can pretty easily guess what's going to happen here. But the objective of this was actually to solve for R. So because of Ohm's law, R is actually equal to delta V over I, which is actually 1 over the slope of this graph. So if we actually look at what the reciprocal slope would be for this graph, the regular slope would be a rise of 0.5 and a run of 5. So that would be 0.1. So the slope of the graph is 0.1. So that means the resistance is 10 ohms. And then plug into any formula of your choice, probably this one, because we give the voltage. So power is just the voltage squared divided by the resistance, which is 64 over 10, or 6.4 joules per second, which is a watt. Now, an easier way of doing this is actually, because this resistance this is a constant resistance, you could have actually just extrapolated your graph out and said that when there's 8 volts of potential difference, there would be 0.8 amps of current. So 8 times 0.8 I delta V gets you same answer. All right, now let's find the current through the 6R resistance. This is a pretty standard circuit analysis question. So anytime you got a combination circuit, you want to find REQ. So we have an R in series with a 3 and a 6. R. This is one that shows up a lot. This is just actually 2 ohms. Or sorry, just 2. So I get 1 plus 2, which is 3R. So whenever you find the total resistance, it's pretty easy to get current, because Ohm's law for the entire circuit says the battery current is the battery EMF divided by REQ. So in this case, it's going to be the battery EMF divided by 3R. And we actually want the current to the 6R resistance. So this is not the answer, because this would be the current up here. This current is 1/3 battery EMF over resistance. But this is a junction point right here. All right, some current is going to go down each of these branches. This is like your drive-through. So it's going to split somehow. Now, to figure out exactly how it splits, we just use Kirchhoff's rules. So we do know 2 circuit things about the R resistor. We know its resistance and we know its current. So delta V through the R is just I, which is the battery current, times R. So we get 1/3 of the battery voltage. So that means we drop 1/3 of the battery voltage across this resistor. So by the loop rule, which says that your voltage drops have to add up around a closed loop, that must mean the voltage drop across the 6R or the 3R is going to be 2/3 of the battery voltage. So that means my I through the 6R is just going to be the voltage drop across the 6R, which is 2/3 of the battery EMF, divided by its resistance, 6R. So, oh man, 2/3 divided by 6, that's 2/18, which is 1/9. Is that an answer choice? Absolutely it is. So that's a pretty standard couple-step circuit analysis. All right, now we'll do the same thing with capacitors. Except this time we want energy stored. So there's 3 energy formulas for a capacitor. U is 1/2 Q delta V, or 1/2 C delta V squared, or 1/2 Q squared over C. So once again, same idea holds, where this time we can find total charge, because the total charge in a network is C delta V for just the entire network. So we can first combine these capacitors. So the equivalent capacitance is just going to be, capacitors actually add in parallel, so it's opposite the resistor rule. So I have 6 and 12, which add via the reciprocal, because I have 1 over 6 plus 1 over the 3 and 9 are equivalent to a 12. And that is, what is that? 4 microfarads. So then we can just plug in for our total charge. So our total charge is C delta V total. So our total C is 4, and our total delta V is 3. So that gives us 12 microcoulombs on the network. So what that tells us is that before the junction rule splitting happens, all 12 microcoulombs are actually on the 6 microfarad capacitor. Now they are going to split, so it's harder actually to ask like something about those capacitors. But we have 2 capacitor quantities, so we can solve for the energy. So the energy is 1/2 times Q squared divided by that capacitor's C. So we'd actually get 12 squared over 12, which is 12. All right, and now we did a R circuit, we did a C circuit, now it's time for an RC circuit. So we want to calculate the steady state charge on this capacitor after a long time. So steady state means the capacitor has became a gap because it's fully charged. So I'm just going to replace my capacitor with a gap or a hole in the wire. So no current can cross the gap. So what that means is that my current is forced around, not a short circuit, but what I've been calling a long circuit. So REQ for the long circuit, because it can't skip down that middle path, so it's got to go through an R, a 2R, and an R, which makes 4R. Then, as a result, we can find the total current in this series loop by doing the battery EMF divided by REQ. All right. Now we can just find the voltage drop across the capacitor. So there's a couple ways of doing this. I find it easy that, once again, what can we know first? Well, we figured out this current. So we can say the delta V across the R is just going to be IR for that resistor. So we get 1/4 of the battery EMF. And then it's just a quick application of the loop rule, because if this is 1/4 of the battery EMF and the capacitor makes a closed loop, this must be 3/4. So why that's helpful is because we wanted the charge on the capacitor, and the charge on a capacitor is Q equals CV. So that means we can just say that Q is equal to the capacitance C times the delta V across the capacitor, which is 3/4. All right, last circuit question. Calculate the time required for the voltage across one of these capacitors to reach 63% of steady state value. All right. Well, anytime you see this percentage, this really only means one thing, right? This means we're solving for the time constant. So the time constant is RC, as long as we're doing the equivalent resistance / capacitance. So we got a 12 and a 6 ohm resistor in parallel. So parallel resistors add via the reciprocal rule. So that's 1/12 plus 1/6 to the -1, which is actually 4. We figured that out in the previous problem with the capacitors. And then we have capacitors in series down here, which also add via reciprocal. And that one is 2 microfarads. So our time constant would be REQ times CEQ, which is 8, and then we pick up a factor of 10 to the -6 from the capacitor. So it's 8 microseconds. All right, now on to magnetism. So magnetic field lines, they always form closed loops. We have this word ferromagnetic for the strong permanent magnets. We call them permanent because ferromagnetic things maintain their magnetization after you remove a B field. But paramagnetic, they'll be magnetic if you have a magnet near it, but then they'll lose magnetization. So because magnetic field lines form closed loops, the net magnetic flux or magnetic flow through a 3D volume is 0. So it's like spheres, cubes, etc. And this doesn't apply to 2D because like you can't really like have a well-defined idea of what like in and out is volume-wise for a loop, right? There's no volume in a loop. Now we have magnetic force. So magnetic force, if it's on a point charge, is QVB. Magnetic force, if it's on a current, is BIL. And an important part of these formulas is it is the perpendicular component that matters. So there's no force if you move parallel to the field. So if a charge moves parallel to the field, no force. If a current is directed parallel to a field, there's no force. And also the resulting force is perpendicular to the direction of travel and the B field. So some people like this version of the right hand rule where you're doing the finger guns like an X, Y, and Z. So you always do get like a 3D coordinate system out of this. I like the point your thumb in the direction of positive charge flow, and then I point my fingers in the direction of the field. And my palm slaps the positive charge where to go. And if I have a negative charge, I use my left hand. So if you have a particle in a uniform magnetic field, it goes in a circle as long as there's a force. And if you're somehow moving at constant velocity in a magnetic field and there is a force, you must have like a balancing E field somewhere. Then for wires, the magnetic field from a wire forms a circle. Our formula for that is mu naught I over 2 pi r. And if you combine this formula for the wire field with the Bill force, you get our Coulomb's law looking idea for the force between parallel currents. And it's actually the opposite rules than charges. So same currents attract, opposite currents repel. Now, if you have moving charges in a conductor, so this is anything with width or length, the magnetic field, due to that QVB force, actually separates charges. And the charges separate until there's an E field in the bar to actually counter that magnetic force. And this gives a voltage that we call the Hall effect voltage or the motional EMF voltage, VBL, where L is the distance perpendicular to the motion. Now, if you connect this bar in a closed loop, which is most commonly seen in like the bar on rails problem, this creates motional EMF where we can use Ohm's law to get the current. And there's always a magnetic drag force. So you could figure out the current, and then you could do QV cross B to do that. But the Bill force always goes against the motion. This is a consequence of Lenz's law, which says the loop is always going to induce a current to fight the change. But just realize this is like goes on the memory list here. The Bill force always fights the motion. Now, motional EMF is also a consequence of this idea of Faraday's law, which says that the magnetic flux piercing a loop, if that changes, that induces a voltage or an EMF. So the rate at which the magnetic field times the area of the loop changes with respect to time gives you the induced current. Induced EMF. Then divide by resistance to get the current. Now, to figure out what direction it goes, your answers are either counterclockwise or clockwise. You have to figure out which way the flux is changing. So if you're getting more X's, more X's, more X's, you need a field that generates circles, for example. Or if you're getting more circles, more circles, more circles, more out of the page, you need to generate into the page field. And your right hand fingers will wrap around. So some common MCQs. We have the basic ferro versus paramagnetic. We have comparing forces / right hand rule. We have the velocity selector. We have where you set QE equal to QVB. We have the net magnetic field from multiple wires. We have the Hall effect, bar on rails, and flux change. So a whole lot of stuff we could ask. Oh, guess we get to know the answer to this ahead of time. When a metal nail is rubbed with a bar magnet, the nail is able to pick up paper clips. If the nail continues to strongly attract paper clips without the bar, what can be concluded about the nail? Well, it must be ferromagnetic, right? Because that's just the definition. If the domains remain aligned after the field is removed, you've got a permanent magnet, and permanent magnets are ferromagnetic. So sorry for spoiling it, I guess. We have these two orientations where a charged sphere moves in a B field. We want to figure out the path taken in each of these cases. So first we have orientation 1. So if I try to do that, I do QV. So my thumb points to the right, cross B, where I got to move my fingers to the right, and I can't do it. I can't do it. And that's not a surprise because the magnitude of the magnetic force on a particle is QV perpendicular B. Well, I have nothing perpendicular to that B field, so I actually have zero force. And then if I try orientation 2, I have QV cross B. My palm points at me, so that actually means it's going to start curving towards me with a force QVB because it's entirely perpendicular. So what do we get? Well, in orientation 1, there's no force. So Newton's first law says it's going to move in a straight line forever. And then in orientation 2, it's going to start curving at me in uniform circular motion, so we get an arc. So we get straight line, then we get an arc. All right, now we got our velocity selector. The small charged sphere moves at constant velocity in the plus x direction as shown. We want to find the direction of the fields. Well, E field is super easy, right? Because E field just goes from source to sink. Then for the B field, well, we got to think about forces. So it actually does not matter what sign of charge this has. The same analysis will work. But we're going to assume it's positive just to make it easier on us. Now, a positive charge would get pulled down because positives go with the E field. So that must mean the magnetic force is directed up. And those must exactly cancel each other. So I just got to figure out how I get a magnetic force up. So in my scenario, my charge is moving to the right, and I want my force to be up. So my palm has to point up. And notice my fingers are pointing at you or into the screen. So that means my B field is into the screen, which is the negative Z direction. All right, now we got some wires. They're the same current, but oriented in opposite directions. We want to talk about the force between the wires and the B field at point P. So what we do know is that we do know like wires attract, but I don't like that one. That's not helpful here. What is helpful, these are opposite currents because one is right and one is left. So these are opposite currents, and we know that opposite currents repel. This is just a fact, although you could figure it out by using the B field from the wires. So my first wire here carries a current to the right. So if I stick my thumb to the right, my fingers pop out of the page above the wire, and then they wrap into the page sort of below the wire. So the blue wire is generating into the page field. And then the leftward current, well, if I wrap my fingers here, my fingers wrap into the page above the wire. So that's also into the page. So I get X's and X's, which make more X's, namely not zero. So I have a repulsive force with a non-zero B field at the center. All right. Now we have a stream of positively charged ions moving in this slab. Also, they could be really mean and talk about current instead of like the charge carriers, and you have to remember it's negatives that move opposite conventional current. If they do that, that's extremely cruel. But hopefully we just give you the sign of the ions. So we have positive ions moving to the right in this case. And I give you all the quantities. We want to figure out the potential difference between the top and the bottom of the slab. So why do we get a potential difference? Well, if I do QV cross B, so B is at me, my palm is slapping these charges down. So these positive charges are going to collect on the bottom of the bar, which means the bottom of the bar is at higher potential because the E field is going to be directed from positive to negative. So that means that the top of the bar is downhill. Now, what's the actual magnitude? Well, this uses the Hall effect formula. We could actually derive this real quick because if the charges are in equilibrium at this voltage, we actually do know that the forces are equal. We know that like QVB is QE, so VB is equal to E. But then we also know that since delta V equals ED, or EL in this case, we could substitute E over L in. Obviously, you could just you could be done with this a lot quicker. So you could say VB equals E over L, but I do think it's a useful exercise to at least derive the Hall effect once. So we get, there's V over, delta V over L. So we get delta V from the Hall effect is VBL. So we can just go ahead and plug in. Delta V is VBL. The speed is 0.08. The B field is 1/4 Tesla, and L is 0.5. So we get an eighth of 0.08, which is 0.01 volts. And we already figured out from the right-hand rule that the potential is higher at the bottom. Now we got our conducting bar on rails. Conducting bar is on these rails. Figure out the power dissipated. So power dissipated is obviously one of these. It's one of our three powers. All of them are the same. But this is a bar rail system. So if you ever see a bar rail system, instantly write this. Instantly. Anytime you see bar rails, VBO is the voltage. And this is similar to last time where you got like your positives that are going to cluster there. You got your negatives that are going to cluster there. So that means we're actually going to get, nope, we're going to get a clockwise current. So what is the current? Well, you could get the current from Ohm's law. VBL over R. And then you can just plug in. But I actually think you could plug in VBL over R for I and then EMF for delta V. But I actually think it's way easier to use this power formula because we know the induced EMF is VBL on these bar problems and the resistance is R. So it's that one. Now to end with our multiple choice section, we got magnetism with Faraday. So the magnetic field perpendicular to a square loop of side length 0.5 meters is plotted below. What's the EMF induced at t equals 1 and t equals 3? So we know that EMF, in absolute value at least, the negative just tells you current opposes the change, is the rate of flux change. And what is flux? Well, flux is BA. So we just got to evaluate this fraction at each of these times. So at t equals 1, that's right here. So this is like the linear slope part. So at t equals 1, the EMF would be, well, what's my change in B field? Well, my B field increases by 1.6 Tesla. And the area of the loop is 0.5 meters squared because it's a square loop. So that means each side is 0.5 meters. And then that change is happening over 2 seconds. So I get 8 times a half, which is 0.2. Now, what about t equals 3? Well, yeah, there's a ton of magnetic field through the loop at this time, but is it changing? Absolutely not. So since the field isn't changing, you have no slope and therefore no EMF. So it is answer choice A. All right, so that wraps up our multiple choice review. So now we're just going to go over some facts that are just worth remembering for exclusive courses. So if you're an E&M, these are the E&M specific topics, and then I'll do the AP2 ones. So if you're looking for AP2 stuff, just timestamp your way ahead here. All right. First up, we got our calculus relationships. So instead of just a uniform resistor, you might have resistivity that varies along the length. You might have to add up all the power to get the energy. You might have to chop up a rod into a bunch of pieces to get its E field or potential. Gauss, this is a big one. The flux through a surface, electric flux through a surface, only depends on enclosed charge. And you can also get magnetic flux by integrating. So this is that case where like you have the wire near a loop and you have to put a bunch of strips down and you integrate and you get some sort of natural log because you're integrating like the 1/r function. We also have the fact that E is the downhill slope of V, which means that your change in potential is how far downhill you walked. We have everyone's favorite, the Biot-Savart law. If that shows up, you're kind of cooked in most cases. It's probably not going to show up. The thing you need to know from this is that B from a loop, so like a circle of current, is mu naught I over 2r. Not 2 pi r, that's the wire formula. So you do have to, that's all you really need to know from Biot-Savart. Maybe there's a fringe case that makes you set up an integral, but you need to know B loop is mu naught I over 2r. So no pi. No pi. So actually making it into a circle actually removes the pi. Then we have Ampere's law. Circulation is proportional to enclosed current. We have the true form of Faraday's law. And then we have our inductance or inductor voltage formula. Technically, there's a negative there, but it's all fine. So one exclusive topic for E&M is charge distributions. This would be, if you need review on charge distributions, this is 4.2 in my notes. So you can go to my E&M playlist for that. If you feel like you need some more help going over the arc of charge, ring of charge, line of charge for the E and V for that, that's section 4.2. Then we got Gauss's law. This would be section 4. What is this? 4.5 is the big one, where you have to find the E fields using Gauss's law. So we always are going to write Gauss's law as the flux can be found two ways. It's EA or it's Q enclosed over epsilon naught. So if you have scenarios of high symmetry, you can always write Gauss's law as EA equals Q enclosed over epsilon naught. The integral is actually misleading, and it really makes you think there's a lot more going on than it actually is. So even though the integral side of Gauss's law looks scary, like this object looks kind of scary, it's not. This is the easy side of Gauss's law, because either E times sphere area, if you have a sphere. It's E times cylinder area, barrel area, if you have a cylinder. Or it's E times 2A if you have that sort of Gaussian pillbox thing with the plane of charge. Again, review those derivations. Now, the most difficult part of Gauss's law is not the integral side, it's the enclosed charge side. So enclosed charge is always, if you have uniform charge density, you can just multiply the charge by the enclosed volume. So if you get uniform, for example, uniform for a sphere, it ends up turning into like Q over 4/3 pi big R cubed is like the total density. And then 4/3 pi times little r cubed is the volume that you enclose. So you get this neat little volume fraction term for uniform that shows up. But then if it's not uniform, you're gonna have to do some integrating. So if it's not uniform, you have to integrate rho, not with respect to r, but with respect to v. So you have to actually break up your volume into little pieces. So here, this would be our dv for a sphere, right? Because The sphere volume is 4/3 pi r cubed, so you take a derivative to get that. And then we have a cylinder here. A tip for Gauss's law is that the differential term is always the same as the flux area term, because the volume of a cylinder is pi r squared projected to distance L. There's also the slab, but we're going to say there's no chance we have an insulating slab. I haven't seen that in many, many years. Now, the magnetic analog of this is Ampere's law, which says that magnetic fields spin around currents, and the amount of spinning is proportional to the enclosed current. So if you have any sort of wire or cylinder, your circulation is B times L is always going to be what our circulation is. So if it's actually an actual circle, you circulate around the circle. And if it's a solenoid or a slab, you take like a half in, half out rectangle on the center. And only one of the four sides contributes there. So look that up. Ampere's law is 4.7. As per usual, we see this mirrors Gauss's law, where it's not the calculus side, it's not the integral side that's hard, it's the density side. So if you got uniform density, you just multiply the current density J by the area A, where the current density J for like a uniform wire would be the current divided by the total area, cross-sectional area, pi r squared. Then you multiply it by the enclosed area, pi little r squared, and we get not a volume fraction because current isn't distributed over a volume, it's distributed over an area. So you get this neat little area fraction. And then if you have a J of R function, you have to actually integrate, where if you have a circular cross-section there, you'd have 2 pi r dr as your area element, and if you have some sort of a slab, you'd have x dz. I don't really expect to see a slab, though. So again, a circle, the area of a circle is pi r squared. So you have to integrate, if you have to find currents, which that's often a question by itself, it's not actually an Ampere's law question. It might ask just what's the total current. So you have to integrate with respect to r, not jr, but j times 2 pi r dr. Now for a slab would be like a rectangle. So like maybe you have like a rectangle whose area is like x times z. This is one of the hardest parts of E&M. It's multi-loop circuits. So you've got multiple batteries. Your only choice is to just Kirchhoff rule grind it out. You can't REQ this. So your rules for circuits with multiple batteries is that if you go with the battery from minus to plus, you gain voltage. So I recommend putting plus and minus signs on everything. And if you go with the current goes downhill. So that would be a drop. So anytime you go with a current, that's a minus IR drop. Anytime you go against the current, that's a plus IR gain. And eventually you'll write enough loop equations to solve whatever you want. I really only see this being like a multiple choice thing. Maybe one question. Now, in addition to capacitor circuits, E&M also has inductor circuits, which just behave the opposite of capacitors. Because inductors are like, oh no, you're not going to change the current through me. So they oppose changes in current. So at a short time, they're a gap because they oppose the change. And then eventually they warm up to the idea, right? I said these are your baby boomers. Inductors are your baby boomers, where eventually they'll adapt to the times. But they're not going to be happy about it. It takes a long time for them to reach steady state. And time constant is L over R, EQ. Now, if you connect inductors and capacitors together, those two are in a constant battle because they have opposite behaviors. So it's a constant battle between the charging of the capacitor and the current in the inductor. And if there's a resistance, nobody ever wins. And the charge on the capacitor, or the circuit, or the current in the circuit oscillates like a sine or a cosine curve. This is the period. That might be helpful to know that. The formula sheet gives you omega. I think the period is a much more useful thing to know. If you're solving for like any circuit quantity that's not time related, you should use energy. So just like with oscillators in mechanics, where we like to set the extreme energies equal to each other, if you pick the time when there's max current and you pick the time where there's max charge, you can just set their expressions equal. This is only true if these are like the max values, but you're not going to be given a different time in E&M. We don't care about that. Now for differential equations, in this class, there's really two diffie Qs you have to do. If it's a circuit, it is 100% Kirchhoff's loop rule. So if you see a circuit and like a diffie Q that says derive blank as a function of time, you have to do the loop rule. Now you do know all functions are either going to be an exponential approach, so they rise and flatten out, or an exponential decay, where they start at some initial value and decrease. So these are your parent functions. Be ready to spawn these in. Unless if you're really fluent in calculus and want to do this every time. Please just memorize these formulas as like the parent function. Now for an RC circuits, the equation is I go through a battery, then I drop some current through my equivalent resistors, and then I drop some voltage. I did say voltage, right? I should drop some voltage across the resistor, and then I drop the remaining voltage across the capacitor. And this is a differential equation because I is the rate of charge flow. Now, I do loop differential equations by I always include the battery term. I always include the battery term because it gets your signs right. So if you have a discharging capacitor that's not connected to a battery, oh, no big deal. I don't have a battery. I just remembered I don't have one. But keep the minus sign. So always keep the battery as like your first line and then get rid of it. Then for inductor circuits, it's the same idea. You gain some volts across the across the battery. You drop some volts across the resistor network. You drop some volts across the inductor, then you're back. There's no transforming needed here because you have I and di dt already. If there's no battery, substitute the battery EMF term is 0. Now, once you have separated, you can feel free to just spawn the solution in. So like if I were to do one right here, like if I had the inductor one, I could rearrange it like this. So I could get di dt equals EMF over L minus I over I times. I can do this. Now I have to separate, so I have to put everything on one side. And then I integrate both sides. So this would be an inductor that starts with 0 current in it and ends with current in it, and we go from 0 to some time t. And then to get my full point, I actually don't need to show any work after this point. I am just apparently some sort of physics visionary because, oh look, here comes the answer. So 1 minus e to the negative t over tau is my parent function, and my steady state value would just be the inductor's a wire, so you just get the Ohm's law current. I do really encourage you to just kind of know these. It saves you a lot of time. This is an absolute headache to solve, and you'll waste a bunch of time on the free response messing with symbols. And you get exactly 1 point going from here to here. So most of the points, so you get a point for the loop rule, a point for separating, a point for integrating, and then a point for the answer. Now, if you have a moving bar, this is the Newton's second law equation, F equals ma, or F equals m dv dt. You have to know these sort of cases of the bar rail system. So if the bar is just getting stopped by the magnetic force, Bill is fighting the bar, nobody's helping. So F net is negative Bill. If you're dropping your bar, gravity's helping the bar move, but Bill is fighting. So you get mg minus Bill. If you're on a ramp, gravity's helping, Bill is fighting, but not all of gravity, because some of the gravity's wasted by going into the ramp. All right, let's do our Physics 2 exclusive topics now. So this is thermo, optics, waves, and modern. So we're just going to go through some facts and things to remember. Because honestly, I don't know how many problems really helps for some of these AP2 things. They're just a lot of like little facts you got to know. It's a lot different than the E&M section where it's problem-based. Like these are very principle based. All right. So for thermo, specific heat is how difficult it is to change the temperature of an object. So this means things with higher specific heat are harder to heat up, but they're also harder to cool down. So I like to think of it as like a thermal inertia. And also, you need to remember the special types of gas processes. Make sure you're good with your vocab here because it makes a big difference. So the PV diagram, the area under this curve gives you sort of the work done. And a lot of things can be easily visualized using this diagram. So an isobar, bar like barometer, is constant pressure. So if my pressure can't change, that is a horizontal line. So we get a nice rectangle for our area under the curve. Isovolumetric, unsurprisingly, is constant volume. So that would be a case where you can't change horizontally, so you have a vertical line. This is no work done, right? Because there's no area. This is just a line. Then isothermal is a constant temperature, which is a curve on a PV diagram because P times V is a constant. Why is that? Well, we know that PV equals nRT. That's how you solve most of these gas problems, is you look at PV equals nRT. So if P goes up, so we know that T is constant in an isotherm. So if P goes up, V has to go down. So we get this sort of reciprocal function. So actually, your product of grid boxes remains constant on an isotherm. I don't know if that's useful, but it's a fact. Then an adiabat, this means no heat is exchanged. This is also a curve on the PV diagram, but it's just lower. It's a lower curve than an isotherm. Not that you'd ever have to compare this because there's some calculus involved to get the isotherm equation. It's like a 3/2 power or a 5/2 power. Now for optics, the angle of reflection is the same as the angle of incidence. If your surface is flat, the rays are going to bounce mostly at the same direction, so you get a nice, shiny, reflective surface. But if you have a rough surface, like paper, your light is going to bounce in all these directions, so it diffuses around, giving diffuse reflection. If your light enters a new medium, the light ray refracts towards the normal. If you have a larger refractive index that you're going into, so like air to water, bends towards the normal. And the converse is also true, right? If you go to a lower index, you go away. Now for ray tracing, if you have the converging type optical instruments that have like real focuses where light is going through an actual focus, if your ray enters parallel to the axis, it goes through the focus on the way out. If it goes through the focus on the way in, it exits parallel. So those two rules exactly mimic each other. And then if you have the diverging case, that means if your rays enter parallel, they exit where it appears that it came from the focus. So it appears that the focus was sort of generating the light. And similarly, if it appears that it came from the focus, it's going to exit parallel. So what does that mean? Here's our pictures. So we see enters parallel, goes through focus, enters parallel, goes through focus, enters through focus, exits parallel, enters through focus, exits parallel. And then we do have a third rule. For lenses, going through the center does nothing. For a mirror, it's flat at the center, so just use the law of reflection. It bounces at the same angle. Then for the diverging, we see the same thing, right? Enters parallel, exits like it came from the focus. Looks like it came from the focus, so it exits parallel. All right, it looks like it came from the focus, exits parallel. And then centers undeflected. Same idea here. There's other ways of explaining this, but it works out. I had some fun latexing these ray tracing rules into that. Then lens equation applies to all these things. Make a negative focus for the diverging instruments because it's not a real focus. More facts that you might find helpful for the converging instruments: real, inverted, reduced if you're beyond 2F. real inverted enlarged if you're between 2 and 1 focal length, and it's virtual upright enlarged if you're closer than 1. For diverging, it's always virtual, upright, and reduced. These facts can save you some time on the claim questions. Wave time. Wave speed is only determined by the medium. EM waves move at c in a vacuum. That comes up a lot. Beat frequency is the difference in frequency between two waves. Polarizers, I like to think of them as like playing like the game hole in the wall, where if you have polarizers where one of them lets in light in one direction, and the other polarizer only lets in light at 90 degrees out of phase. If you have one polarizer, you get about half the light going through. If you do the other polarizer, you get about half the light going through. But since this polarizer forces them to go in a certain direction perpendicular to this one, you actually get no light if you cross polarizers like that. I don't know how big this is in P2. Just know that fact. Know that if you have the crossed polarizers, you get no light. Because light is assumed to be randomly polarized. So if one polarizer forces you to be straight in one direction and the other one lets none of that direction in, it's obviously nothing. Then Doppler shift, you need to know frequency increases when you're moving closer together. Right? Think about just the ambulance, right? It goes by you like, right? It's higher when it's going towards you, and then it decreases. This is one of the only things that goes on the P2 memorize list. I think it's important that you memorize the standing wave conditions. So this comes from the fact that waves reflect at boundaries. So if you have a boundary, part of the wave can go through the boundary, the other part reflects back. And if you enter a denser medium, the reflection also is upside down. And as a result, if you keep sending sort of these air or pressure waves through a pipe, they're going to continue to add and to construct and destruct. And it ends up working that there's only specific values that you can have for these standing waves. And if it's open, open, or closed, closed, you have a situation like this, where you're allowed basically to have maximum wiggling or minimum wiggling at both of these points. So if you try to connect that, that's like peak to trough. So that's exactly a half wave. But if you do open closed, one of your sides is fixed, so there's no wiggling, and the other side is open, so there's maximum wiggling. So you go from 0 to peak, and that's a quarter cycle. Because if you think about what a wave could look like, it could be something like this. So with the open, open, or closed, closed, you have a situation like this where you're peak to trough, which is a half, but open and closed, it's a quarter. Now, all of that is just to say that you get half wavelength multiples that can live in the closed, closed, open, open, and you can get quarter multiples that are only odd. Why is it only odd? Well, if you have the even ones are actually just the open, open, close, close. So you know it can't do that because they have to be different. Now, if you want the wavelengths instead, just do V equals lambda F and mess with it. You're basically just reciprocating some stuff and dividing out the V. Remember this, right? Wavelength and frequency are inversely related, right? If I extend a trombone slide, the frequency goes down. Now, for general interference, it's all about path length difference. So if two waves meet and they've traveled exactly one wavelength, two wavelengths different from each other, well, peaks and peaks line up, troughs and troughs line up. But if they're half wavelengths out of phase, that means peaks and troughs line up, so they cancel. So these are our conditions for interference. And a result of this is you can get diffraction. And diffraction is really straightforward in P2. Just plug and chug into the formula. But to save yourself some conceptual time, since path length difference is proportional to wavelength, your long wavelengths have to travel larger distances before you get that difference. So red diffraction patterns are spread out, while violet diffraction patterns are close together. This is a really tricky topic, but it's important to include. For thin films, this is an interference that sort of combines with refraction, although P2 is just about incident with the normal, so no Snell is really needed here. So this is like going through a film where like you have sort of three layers where you have like something, film, and then something else. So if you think about what's happening is like some light ray is going to reflect and hit your eye here, but then another light ray is going to go through the film and back and then hit your eye there. So the difference in path length, if we're looking normal, is going to be 2t because it has to go in the film and it has to come back. And then another thing is we have to take into account that if you approach a boundary and you go into a denser medium, that pulse reflects. So if you go to a higher index of refraction, every time your refractive index goes up, the conditions swap. So if I'm looking for destructive interference, which is originally this, anytime I go to a higher index of refraction, I have to swap the conditions back and forth. So for example, if I'm in a vacuum, which is n equals 1, and then a film, which is 1.5, and I'm looking for destructive interference, well, I've approached the film, so I know that my conditions swapped once. And then I approach a different thing, but there's not a reflection, there's not a phase shift across this one because it's not a larger index. So I've exactly swapped the conditions once. So this tells me my destructive condition is actually a whole wavelength. And another subtlety that definitely comes up with thin films is it is not the wavelength in the vacuum you have to use for the path length difference, because the path length difference comes from moving in the film. So you have to do wavelength in the film. So you do actually need to know that the frequency is the thing that's the same in the film. So you end up getting this fact that like the lambda in the film, you have to divide by the refractive index, because you know that the speed in the medium, which is c divided by n, is equal to lambda in the film times f. And for the frequency to remain constant here, we know we have to have this division by n on this side too to make it work out. All right, last thing, we got some modern stuff. I can't imagine too much with modern that involves concepts that are super involved. Black body, know that since higher frequency equals higher energy, it makes sense that the hotter black bodies peak at lower wavelengths. And for nuclear reactions, make sure to conserve nucleon number. That's like your atomic mass number. And charge is conserved, which is like the, I'm not going to call it just atomic number, but those also have to add up on both sides. So like you might have to add like positrons or things. Decay is exponential, not linear. So if you're looking at things like half-life, after one half-life, you have half remaining. After two half-lives, you have half of a half, which is a quarter, then half of a quarter, which is an eighth, and so on. Modern is usually pretty straightforward. Then for energy levels, remember you only get certain energy levels allowed. So we have quantized orbits according to the Bohr model, which means you can only absorb certain photon energies that bump your electrons up a level, or you can only emit photons by allowing your electron to drop between certain energy levels. And this is why colors are unique for each spectrum of elements we see, because the energy of the photon, which is determined by the atomic orbital levels, determines the frequency, which determines the wavelength, and therefore the color. All right, now our FRQ discussion here. For the MR question, that's our first free response. This is draw something, derive something, make a claim in AP1 or AP2, and then derive something again for APC. FRQ2 is the more like involved one where you got to draw, derive, graph, and make a claim. Then you got your lab question. We're probably pretty familiar with this at this point. Look at my practice test if you want to see how these work. I'm sure that we're pretty good with this, though, if you're in P2 or APC. Probably seen these. So you got our lab where you got to talk about measuring, explain how to solve for something. Then you got to solve some cookie cutter experiment they give you data for. Then with the QQT, make a claim, justify it without math, do some math, and make a claim or say they're consistent or not. Now, here's kind of what I've noticed for test distributions. For E&M, it's pretty well established that you get an electrostatics question. So that's either charges, which is Coulomb's law, rod, ring, or arc. which is charge distributions, or Gauss's law, which is spheres or cylinders. So you'll get one from this category. Then you'll get one circuit category. Resistors, RC, LR, LC. Sometimes they mix these two. Then you got magnetism only. So this is like velocity selector, charges in a magnetic field, wires interacting with each other, or Ampere's law. And then you have induction, which is either Faraday's law with functions or it's a bar rails question. So if I were to predict this year, last year we actually got a Gauss's law question involving capacitance with a cylinder. This was like a coaxial cable. So I'm not totally sure if we're going to see Gauss again. It was just a small part of it, so I wouldn't doubt it. I'm actually feeling more strongly we'd get like an energy-based charge distribution question. This is kind of my pick. So like maybe you have to find the potential, and then you have to do some like kinetic energy stuff. That might be my guess there. Although I also wouldn't be surprised if we have Gauss's law with a rho of r. So my second pick is that we get like a density function rho of r, Gauss's law with a sphere. But I'm going to pick charge distribution. I might guess it's something with like a rod where you have to integrate some stuff with the rod. Maybe find E field or potential, and then you got to find like the speed when you're really far away or something. Then it seems like we've really been lacking LR circuits for E&M recently. So I feel like we're going to get one of the RC or LR. I feel more strongly about LR because it's been longer, but they're practically the same. So if you prepare for LR circuits, you know how to do RC circuits. It's just a different time constant and different long-term behavior. And then we had wires last year. So unless if it's like a forces question with wires, like we had a pure B field question last year, I feel like we might actually get like the mass spectrometer or the velocity selector this year, or we're going to get Ampere's law. But actually, since we're not going to get Gauss's law in my like prediction, I think we might get Ampere. So I'm guessing we get exactly one of these. One of Gauss or Ampere. So I'm going to guess we get Ampere. Although I'm not surprised if we get like a B field problem with the spectrometer. Then I feel like we're going to get the bar rail system. I don't know if that was on many of the forums last year, if any. That might be my spot to do a diffie-Q. So this could be a big diffie-Q year if they do the LR circuits and the bar rail system. Because last year on the released form, you only needed calculus on 2 of the 4. You needed to take like one derivative and then do one integral. So yeah, that tracks doing calculus. Oh, this would be calculus on all 4. I don't know about that. Maybe I take my claim away from Ampere and think it might be B field spectrometer. I'd prepare for the spectrometer anyway. It's nice and easy. Those are my picks there. So we'll see what my batting average is. I'm usually quite wrong. Now for P2, it's sort of more compartmentalized, but also not. So it seems like they pick either electrostatics or circuits. I'm more leaning towards electrostatics because we didn't see it last year. We had a wires question last year, so I don't think it's that. And I'm actually going to go bar rails again. I'm going bar rails again. We haven't seen bar rails. So I actually think this accounts for the fact that we won't see circuits. So if we don't see circuits this year, I'm going to guess they're going to do some Ohm's law stuff with bar rails. So maybe VBL stuff. And then you got to pick usually one, like regular optics or wave optics questions. They hit diffraction last year. I might go out on a limb and say they could pick something with thin films because you can do a lot with thin films. This would be like an interesting derive question, but I feel like we might see some standing waves. This year. Now I could see a really interesting question where you might have to like draw some standing wave patterns on the TBR and derive like some fundamental frequency stuff. Like that would be really interesting. I don't know if we see that, but I feel like we might see standing waves. But there's a lot of cool stuff from these categories. And then, do I want to pick against thermo? Like modern is such a small part of the curriculum. I can't really imagine they do a lot with modern. So I feel like we have to do a thermo question. I feel like I have to say there will be a thermo question. If I were to guess, last year was about PV diagrams and stuff. So this year it's probably about more of the other stuff. Maybe some specific heat conductivity type thing. But honestly, I could kind of see anything. Maybe we get like black body radiation or a Vine's law, something like that. We'll see. P2 is such a toss up. There's a million things. It's very hard to like prepare because there's so much in P2. It is actually my favorite of the 4 courses because I think I'm not. There's so much extra like calculus garbage in APC. I would much rather be doing waves and optics. All right. Hopefully that is helpful. Hopefully we at least are going to prepare a bit better. Like this might not have taught literally everything in the courses. Of course it didn't, but hopefully it helped you see kind of where you're at. And some things that I thought are just helpful, quick concepts that might help you bubble a multiple choice you wouldn't have gotten earlier. So, may the odds be ever in your favor.